at our schedule, we have do 3 more classes, 3 more new material classes, followed by a review for the final exam. And then our final exam is Monday, the 21st at 1 p.m. in this classroom. Okay, so we are section C. So there were 3 different sections listed on the syllabus. If that was confusing, just cross out A and B, right? We're section C, 1 p.m. on Monday, the 21st. The 21st, yeah. So between now and the final exam, the only thing that I'll be collecting from you is Project 4. Okay? Project 4 is just a is sort of final exam practice, right? So this is 16 given example of style questions, right? You've had these on every test and every quiz, so there will definitely be some of these on the final, and this is to get you some practice with those. Okay, our last 3 lectures are going to be dealing with exponential and log functions some more, right? So there's no like brand new topics before the final, but we're going to be doing some word problems with exponential and log functions, and we're going to be solving equations today with exponential and log functions. All right, so I'm just going to skip the preview exercises. We'll go to the demo. You can go back and do the previews later if you have time. An exponential equation is an equation, meaning there's an equal sign in there somewhere, right? Where the variable or the unknown is in the exponent. So let's take a look at how to solve an exponential equation using logarithms. So my first equation is going to be 2 times 5 to the x equals 50. Step 1 is to isolate the exponential expression, right? I want to isolate the 5 to the x. So what should I do first if that's my goal? Divide by 2. Divide by 2, divide by 2. So I get 5 to the x equals 25. Okay. Step 2 is to take the natural logarithm of both sides of the equation. Okay. You can actually take any base logarithm of both sides, but the natural log and the common log are nice choices because our calculators have buttons for those. Okay. You probably can answer this question in your head right now, right? 5 to what power gives you 25? 2. Good. So we all know the answer is going to be 2. Let's just see how logarithms can help us get to 2 and then we can use this technique when the answer is not so obvious. So we take the natural logarithm of both sides. So I'm going to take the ln of 5 to the x, and that should equal the ln of 25. Okay, so that's a legal move, right? Because as long as you do the same thing to both sides, the equation is still true. So I took the natural logarithm of both sides. Step 3 is using the properties of logarithms. I want to simplify the left-hand side, right? Anybody remember the property that deals with taking the log of something to a power? You can take that power and put it down in front, right? So I can take that exponent of x and bring it down in front, and it becomes multiplication. So this is going to be x times the ln of 5 equals the ln of 25. Now I can solve for x. You just have to keep reminding yourself sometimes, ln of 5 is just a number, right? You could type it in your calculator and give you a decimal, right? ln of 25 is also just a number. So to get the x by itself, I'm just going to divide both sides by the ln of 5. And ln 25 and ln 5 are just numbers. So x is ln 25 over ln 5. And I can put that in my calculator. And I would get that is an exact answer. And let's see what happens if I put it in my calculator. So I hit the ln button, 25 divided by the ln of 5, and I get 2, right? Which we knew that was going to be the answer. Equals 2. All right, so we should go back and check, right? We should do a quick plug that 2 into the original equation. So does 2 times 5 squared, does that equal 50? Yeah, check. So it's a neat little trick that you can use logarithms for. When the exponent isn't a nice integer that it's easy to come up with the answer in your head, this trick with logarithms, taking the ln of both sides, can be really helpful. All right, so that's how you solve an exponential equation. Let's look at a logarithmic equation. A logarithmic equation is just any equation that has a logarithm in it. So the goal for solving a logarithmic equation is to convert it to an equivalent but easier to solve exponential equation. So you may need to do some manipulation using rules of logarithms before you can do the conversion. So step 1 is to isolate the logarithmic expression. So I want to get the log of 5x by itself. What should I do first? Divide by 2. So I get the log of 5x equals 2. What base is there but not written? 10. Yeah. If you see no base, there's a little hidden 10 right there. All right. Step 2 is to rewrite this as an equivalent exponential equation. So my base is 10, right? What's my exponent? The 2, and that should equal 5x. Step 3, solve for x. What is 10 squared? 100. 100 equals 5x. Divide both sides by 5, and you get x equals 20. Oh, what did I do? I messed. Okay. Oh, I messed something up. Where did I do it? That looks better. All right, and then 10 squared. Okay, so let's check. In our original equation, I want to replace the x with a 20 and make sure it's true. 2 times the log of 5 times 20, does that equal 4? All right, well, let's simplify the left-hand side. 5 times 20 is a 100. What is the log of 100? 2. You could type it in your calculator because you have a log button on your calculator. Or you can remember that there's a little hidden base there of 10, right? And it's asking you what exponent do you put on the 10 to make a 100? A 2. So this says 2 times 2. Does that equal 4? Yes. So our solution works. Yeah. Say that again. Why can't I subtract what? Log of 5? What about the x? Oh, okay. So we've got 2 log 5x equals 2. So you're saying that's 2 times log 5 plus log x. That is true. But this actually makes it harder to solve, right? It's, yeah. Yeah, that's true. Log of 5x does equal log of 5 plus the log of x. But since our goal is to isolate a single logarithmic expression, right? Our goal is to get to something that looks like that so that we can switch it to an exponential, right? So expanding is not going to be helpful while it's allowed. It's not going to help us get to our goal. Yeah. The log button is base 10 and the ln button is base e. So log x equals y means, what am I doing? Means 10 to the y equals x. Right? Whereas the ln of x equals y. With ln, you have an imaginary base e. This is log base e. So this says that e to the y equals x. E is a number. It's an irrational number. It's 2.718. It's kind of like pi. It goes on forever, never repeating. Sure. Yep. Your calculator has an E button also. So if you don't want to round it, you can just press E on your calculator. Right. Yep. Okay, so in our first example where we solved the log equation, we didn't need to use any properties of logs when we were solving that equation, right? So, however, sometimes we have to use properties of logs in order to isolate a single logarithm on one side of the equation. So these were our properties of logs, just to remind you, right? So let's do an example. So what's different with this example and the previous one is that I have two logarithms in this equation instead of just one. So I want to get all my I would like to isolate my logs into a single logarithmic expression. So I want to squish them together. So first, let's put all our logs on one side of the equation. Okay. So I'm going to add log base 2 of x to both sides. Okay, so I have 2 equals log base 2 of 4x plus log base 2 of x. So now I have a sum of two logarithms. They've got the same base, right? They're both base 2. How do you squish a sum of two logarithms into a single logarithm? Multiply them. Yeah. So you write a single logarithm where you multiply the inputs. So I'm going to have 2 is log base 2, and then you do 4x times x, and you get 4x squared. So now I have finally written this as a single logarithm equals a number. So now I can convert this to an exponential equation. What's my base? 2. What's my exponent? 2, and that should equal 4x squared. And now I can solve this equation. Right, so 2 squared is 4. 4 equals 4x squared. If I want to get the x squared by itself, divide by 4. So my next step is going to say 1 equals x squared. Square root both sides, and I get x equals plus or minus 1. Correct. Condense and rewrite. Yep. Let's check our solutions, especially when you get two solutions. You got to check them because one of them might not actually be a solution. Okay, so let's go back to our original equation. 2 minus log base 2 of x. I'll do it on another page here. 2 minus log base 2 of x equals log base 2 of 4x. And let's check x equals 1. So I'm going to put in 1 for all my x's. So I have 2 minus log base 2 of 1. Does that equal log base 2 of 4 times 1? All right, so we're going to simplify the two sides here. What is log base 2 of 1? 0. This is asking you, what exponent should you put on the 2 to get a 1? 0. 2 to the 0 is 1. Anything to the 0 is 1. So this is 2 minus 0. Does that equal log base 2 of 4? I just did the 4 times 1 there. What is log base 2 of 4? 2. It's asking you what exponent do you put on the 2 to get a 4? 2. And 2 minus 0 is 2. Check. Okay, so 1 is a solution. Let's check negative 1. 2 minus log base 2 of negative 1. Does that equal log base 2 of 4 times negative 1? Okay, simplify the two sides here, and I have 2 minus. What exponent can I put on a 2 to make a negative 1? Two to what power would give me negative 1? Radical negative 1, you mean I? 2 to the I is not negative 1. The base has to be 2. 2 to what power gives you negative 1? A half? Let's see. If I raise 2 to the 1/2, 2 to the negative 1/2, 2 to the negative 1/2. Nope, that's not negative 1 either. Negative 2, 2 to the negative 2, a quarter. There isn't any. Yeah. Negative 1 is not a solution. You can't take the log of a negative number, because think about what the graph of 2 to the x looks like. We've graphed it many times. It looks like this. Its range is just from 0 to infinity, right? You can't get a negative number as the result of doing 2 to the something. Okay, so this is undefined, this expression right here. You can't even plug it into the original equation. So that means negative 1, not a solution. That's an extraneous solution. Okay, so we go back to where we wrote our solutions, and we got to take out the negative 1. Okay, so you can go ahead and start your activities.